One of my students asked me, "Sir, why is it that a quantity raised to the first power equals to itself?" To explain, I made this video. Let's go.
Okay, hello and welcome everybody. So in this quick lesson we want to build an intuitive understanding of exponents that are integers. So we mean positive integers, which are the counting numbers or natural numbers, 0, and also the negative integers. So we want to understand what's happening with these intuitively. So let's start off with the number 3. So you would remember from previous videos, and we're going to do 3 squared here. So you remember from a previous video, I would have pointed out that the natural number exponent signify how many times the base is being multiplied by itself. So in this expression, this 2 is saying to us, hey, there are 2 3's, 1, 2, being multiplied together. Alright, if we had 3 to the power of 3, this would mean that there are 3 3's, 1, 2, 3, being multiplied together. And of course, 3 to the 4th power would mean there are how many 3's? Right, there are 4 3's being multiplied together. So there is 1, 2, 3, 4. There are 4 3's being multiplied together. Now, what do you notice? There is a pattern, and math is all about patterns and relationships. The pattern is that as we increase the exponent by 1, we are multiplying a 3 to what we had before. So as we increase the exponents by 1, we are multiplying another 3. Now, what if we were going down and decreasing the exponent value by 1? Let's see. So 3 times 3 times 3 times 3, of course, equals 81. Now, if we were going downwards, we would not be multiplying by another 3. What would we be doing? We would be dividing by a 3 if we were going downwards. So 81 divided by 3 would produce a result of 27. Now look at this. 27 does indeed match 3 to the 3rd power, which is equal to 3 times 3 times 3. 3 3's 9, 3 9's 27. So look at that. The pattern is being established here. As we go downwards, we are dividing by 3. So let's continue. So we're going to divide by 3 again as we go downwards. So 27 divided by 3, of course, we all know that's 9. And look at this. 9 clearly matches 3 squared, right? 3 times 3. Let's not stop there. Let's go further. So we are dividing again by another 3. 3 into 9 goes, you got it, 3 times. All right. So on the exponent side, if we are going to reduce the power of 2 by 1, what power are we getting here? We're getting 3 to the 1st power. Now 3 to the 1st power would suggest that how many 3's are being multiplied here? There's just 1 3. Now look at this. 3 to the 1st power equal 3, and it matches the 3 that we got here as we were dividing coming down. So this can give you an intuitive understanding as to why it is that a base raised to the 1st power is equal to itself. Well, I don't think we should stop there. I think we should continue. So what if I decide to continue dividing by 3 as I head downwards? Now 3 divided by 3, of course, would produce a result of 1. Now with the exponents, if we reduce the exponent of 1 by 1, we'll be getting 3 to the 1 minus 1, which is 0. 3 to the 0. Now based on the laws of indices, you would have learned 3 to the 0 power is equal to 1. And look at that. Now it is clearly matching with what we had here as we developed the pattern. Alright, so a number or a base raised to the 0 power is of course equal to 1, as long as that base isn't 0. But I don't think we should stop. I think we should still continue. So let's divide by 3 again. So 1 divided by 3 of course would result in 1 divided by 3, which is the same thing as 1 over 3. Now as we reduce the exponent by 1, we would be getting 3 to the negative 1, of course, because 0 minus 1 is negative 1, right? And the laws of indices tell us that that means 1 over 3 to the first power, of course, which is just 1 over 3. Now look at that. Isn't this beautiful? We are seeing a clear match here with our pattern that we were developing. So the law of indices does hold true for this negative integral exponent, and it also holds true for this 0 index. Let's try one more. So we're going to be dividing by 3 one more time. So this is 1 over 3 now divided by 3. And of course, if you calculate that using your calculator, or if your brain is as good as or better than mine, you know 1 over 3 divided by 3 gives you 1 over 9. Now let's reduce the exponent power on this side by 1. That would give us 3 to the negative 2. And the laws of indices tells us that it would be 3 to the 1 over 3 to the second power, which works out to give us 1 over 9. And we can clearly see that it is matching right there. So this is one way you can intuitively understand what is going on with integer exponents. There's another way I'd like to quickly show you before we end here. I am going to erase all of this. It is pretty similar, but I don't want all of these to be in the way, confusing you. So let me get them out of the way. I think I need a bigger eraser, but we'll get there. Almost there. Right. So let's start back again with 3 squared. So another way of looking at this is that we can include the unseen factor in this multiplication. And the unseen factor in multiplication tends to be 1. Alright, so we include that 1 in the multiplication, and we have 3 times 3. So of course, when you multiply 1 to anything, it doesn't change the value. So it's the unseen factor in all multiplication. So of course, we still have 2 3's being multiplied together. Now we are including the unseen factor of 1. So let's continue. 3 to the third power would be 1 times 3 times 3 times 3. And 3 to the fourth would of course be 1 times how many 4's? By how many 3's, sorry? 4 3's. So that's 1, 2, 3, 4 3's. Alright. So how about 3 to the first power? So we start with 1 again, multiplied by how many 3's? 1 3, just 1 3. And what does that work out to be? That works out to be 1 times 3 is 3. So again, we are seeing that a base raised to the first power is indeed equal to itself. But how about the 0 power now? So 3 to the 0 power. So let's start off with 1 again, as we said. So 1 times how many 3's? Well, times no 3's, 0 3's. So it's just 1 by itself, which means 3 to the 0 power is indeed equal to 1. So now you can clearly see that the 0 power produces the result of 1. The factor, the multiplication factor remains in the situation here, and there is no, the base is not visible because the power says there should be no base. So only the factor, the multiplication factor is there, which is 1. So let's continue. So now we have 3 to the negative 1 power, since as we have reduced the exponent by 1 again. Now, what does this mean? So let's start off with our factor, 1. Now, the negative exponent would not mean the same thing as the positive integral exponent. The positive exponent told us that we are multiplying by a 3 each time. Now, the negative exponent therefore means we are doing the opposite of multiplying by 3. It means that we're doing, what are we doing? We are dividing by 3, right? Since as that's the opposite. So it would be 1 divided by 3, which works out to be 1 over 3. And of course, that holds true with the laws of indices, because the laws of indices says that 3 to the negative 1 is equal to 1 over 3 to the first power, which works out to be 1 over 3. So we can clearly see here that the result from the laws of indices is definitely matching our pattern over here. And let's try one more. So we have 3 to the negative 2. So this now means, well, we're starting off with our factor of 1 again. Now, how many 3's are we dividing by this time? We're dividing by 2 3's. So it's 1 divided by 3 divided by 3, which of course will work out to give us 1 over 9. Now, the laws of indices dictate that 3 to the negative 2 would mean 1 over 3 squared, which is equal to 1 over 9. And doesn't that look beautiful? We are clearly seeing here that the laws of indices hold true to the pattern that we are seeing here as we operate on our base using these integer rules, or this integer pattern.